previous lecture we looked into a different problem which is an application of divide and conquer, and the problem was about counting inversions. So, in that previous lecture we have looked into one solution of this counting inversions, and for the today's lecture the agenda is to look into the optimized method of solving this problem of counting inversions. So, first we will take a quick recap of this counting inversion and the method which we have already covered, and then we will proceed with our kind of our next optimized method. So, counting inversions, when we say it is going let us say we have been given an integer array of size n, and we need to find the inversion count in the array. So, two array elements, let us say ARR of I and ARR of j, are going to be called as an inversion, are going to form an inversion if ARR of I is greater than ARR of j and I is less than j. And here is an example of that particular kind of a small array which we have seen. So, here 4 is actually greater than all the 3 elements. So, 3 inversions counts contributed by 4. Looking at 3, we have 2 inversions counts because it is contributing for 2 inversion counts. The 2 elements on this right side of 3 are less than 3. For 2 it is 1, and for 1 it is the rightmost element, so obviously 0. So, in this way we are going to count the inversion, and this is going to give us degree of, I can say, sortedness, or this is also being used in the similarity metric. Now, how to solve this counting inversion problem? We have seen naive method of counting inversion problem, looking for all those pairs I comma j with the help of 2 nested loops in which I is less than j, but ARR of I is less than ARR, I is greater than j, but ARR of I is less than ARR of j. And the time complexity which we have seen for that method was order n square because of the presence of 2 nested loops. Now, if we look into the mathematical formula for what is going to be the total number of inversion counts in a kind of, we can say, maximally unsorted array like this, which is available on the screen, 4 3 2 1. So, it is going to be n into n minus 1 by 2. So, that is the count. Now, moving further, in previous lecture we have seen one method which was order n square, and here we are going to look into an efficient method to count the inversion, and this method is giving us the time complexity of order n log n. This method is going to use the merge sort method or the merge sort technique. Actually, this method is going to count the inversion using kind of tweaked merge sort, we can say, or a little modified merge sort. But if I am talking about the merge sort, that means the space complexity is going to be at least order n. So, time complexity order n log n, but space complexity order n. What is the idea of this efficient, or we can say optimized method? So, we are going to use merge sort to sort the array. Now, recall merge sort. In merge sort, we are going to divide the array into equal parts till your each and every array is going to be a single element, and then we start them, then we start merging those array. So, here we will be using merge sort to sort the array, and the kind of, we can say, the modification is in the merging part. So, while merging the two halves, we are going to count how many elements from the left half are greater than the elements from the right half. So, basically these are my cross inversions. Apart from these cross inversions, we also need to look into the individual inversions of the two separate arrays, which is the left array and the right array. So, by counting all those inversions, we are going to solve our problem of inversion count. So, the working of this method says if ARR of I is greater than ARR of j during merging and I is less than j, then all the remaining elements in the left from I onwards will also be greater than ARR of j, because we have this is the thing which we are going to implement while merging. That means if we are at the process of merging, the array is kind of sorted, we can say. So, by using this technique we can count multiple inversions at one. What do we need to do? While merging we need to check if ARR of I is greater than ARR of j while I is less than j. So, then remaining all the elements in left from I onwards will also be greater than ARR of j. So, let us see this with the help of kind of example. So, example I am going to take here one simple example, and then maybe kind of one a bigger example I will also be taking. So, here array is 4 3 2 1. Now, if we are into the process of merge sort, what are we going to do? We are going to divide this array. So, in dividing this array, we are dividing the array into two halves, which is 4 3 and 2 1, and now moving forward we are again going to divide, or we are again going to split these arrays of 4 3 and 2 1 in a recursive manner, and we are having 4 separately, then 3 as an different array, and also two different arrays consisting of 2 and consisting of 1. Now, at this point your each and every array is having having one element. Now, if I am doing some merge sort thing, what is my next step? My next step is to merge these two arrays. So, in merging we keep our order, the sequence, we take up our sequence, we can say. So, if I am going to merge 4 and 3, the ideal or the correct merging should be 3 comma 4. If I am going to merge 2 and 1, the merging should return 1 and 2. So, that is what it is. Now, in order to merge these 4 different arrays of 4, 3, 2 and 1, these are the elements available inside the arrays. So, we will start the merging, and similarly simultaneously we will start counting the inversions. So, whenever we are merging 4 and 3, we are comparing 4 is greater than 3, and it will it is available in the left side array. So, yes, it is going to contribute to an inversion. So, count of the inversion is 1. So, merged array is 3 comma 4. So, inversion was 4 comma 3, and total inversions so far which we have seen is equals to 1. Coming to the next step, which is merging of 2 and 1. The similar situation arises here also. We need to compare 2 and 1. 2 is greater than 1, available on the left side of 1. So, that means it is contributing to an inversion. Count is equals to 1. Merged array which is being returned is 1 comma 2, and but the inversion was 2 comma 1. Total inversion so far is 2, one from this particular step and one from the merging of 4 and 3. So, total inversion so far is 2, and as far as the output at this stage is concerned, we have two merged arrays, one is 3 comma 4, another one is 1 comma 2. Now, what do we need to do? We need to merge these two arrays again and count for the inversion. So, in our next step we have two arrays which are 3 and 4 and 1 and 2. So, we have these two arrays left and right, and we want to merge them. Let us start with 3. So, 3 when compared with 1. So, we are going to take the first element of both the arrays. 3 when compared with 1 is going to give us an inversion count. So, 1, let us say we are shifting to the when we are shifting to the final output array. Now, 3 when compared with 2 is again going to contribute to an inversion count. So, when we are comparing 3 with 1, that is an inversion. When 3 compared with 2, that is also an inversion. Looking at 4, so it is going to contribute 2 inversions. Looking at 4, so 4 when kind of compared with 1, it results in an inversion. 4 when compared with 2, it also results in inversion. So, we can take it this way also. When comparing 3 and 1, it is an inversion. When 3 compared with 3 and 4 compared with the count, so count is going to plus 2. So, the earlier count was 2, and when we are comparing 3 and 1, the count is incrementing by 2. When we are comparing 3 and 2, the count is again incrementing by 2, and the earlier count was 2. So, final merge is what we are going to get is 1, 2, 3, 4, and in this way we are kind of able to get the whole count, which is nothing but overall total inversion count is 6, which is the 2 from the earlier steps, and then 2 and 2 from the next steps. What are the inversions available here? 3 1, yes, is an inversion. 4 1 is also an inversion. 3 2 is an inversion, and so is 4 2 in this last previous step when we are merging 3 4. So, 3 1 is an inversion, 3 2 is an inversion, so is 4 1 and 4 2. So, by this step number 4, the total inversion count contributed are 4, while the 2 were earlier available in the earlier step number 2 and step number 3. So, 2 plus 4 is going to give us a total count of 6 inversions, or overall total 6 inversions are there. So, basically what we have done here, we used our merge sort, normal merge sort technique, and in merge sort we kind of we did the partition in the manner in which we do in our merge sort. Here we are not going to change the partition as of now. So, your partition step is going to give one element in kind of we can say each array, or your merge sort is going to give this. Now, we need to merge the elements. While merging, we are going to count the inversion. That means we need to tweak, or we need to modify our step or our function or the module of merge, we can say. So, here in this example, the final output, or we can say the total inversions were 6. So, the inversion count was 4 and 3 when merged, 1 inversion was counted. 2 and 1 when merged, 1 inversion was counted. Then at next step, when 3 and 4 and 1 and 2 are merged, 4 inversions were counted, giving us a total of 6. So, I am sure by this time now you have got an intuitive idea or of how we are going to use this method of we can say modified merge sort in counting the inversion. So, what we did till this point is we have used merge sort for this. First we divide the array into 2 halves, left halves and right halves, and then we recursively count the inversions in kind of both the halves. While merging the 2 halves back together, we also count how many elements from the left half array are greater than the elements from the right half array, and these represents the cross inversions. So, basically if we are going to kind of describe it in an algorithmic manner, we are going to have kind of 3 kinds of basically we can say 2 kinds of inversions. One is a normal inversion, that is within the left half of the array or within the right half of the array, and another one is the cross inversion which says how many elements from the left half array are greater than the elements from the as compared to the elements of the right half array. So, if we are changing the array, that is kind of, we can say, are the cross inversions, and those cross inversions are going to be identified in, in our merging process. And finally, we are going to sum the inversions from the left half, from the right half, and the cross inversions also, in order to get the total number of inversions in the array. So, this approach efficiently counts the inversion while sorting the array. So, when I am talking about these three inversions, the inversions in the left half and the inversions in the right half, how this is going to work. So, the previous example which we have taken was 4, 3, 2 and 1, it was a small example. In order to kind of taste a flavor of the left half inversions, the right half inversion and the cross inversions, let us take a look at kind of a little bigger example in which we have sorted, in which we have given a list in for which we need to count the inversions. So, the list here is 1, 5, 4, 8, 10, 2, 6, 9, 12, 11, 3, 7. Now, what are we going to do? We are going to divide this list into two sub lists of equal size. So, one as you can see is in blue and another one is in the red. So, the blue list, the elements are 1, 5, 4, 8, 10, 2, 6, 9, 12, 11, 3, 7. Now, if I want to count the number of inversions in the blue list, so let us say 1 and 5 no inversion, then 1 and 4 no inversion, 1 and 8 no inversion, 1 and 10 no inversion, and then 1 and 2 no inversion. So, 1 is at its kind of perfect place. So, if we are looking into let us start from 5 and 4, yes, there is an inversion. So, 1, 5 and 8 no inversion, 5 and 10 no inversion, 5 and 2, yes, there is an inversion. So, 2 inversions as of now. Taking 4, so 4 and 8 no inversion, 4 and 10 no inversion, 4 and 2, yes, there is an inversion, 3, then 8 and 10 no inversions, 8 and 2 there is an inversion. So, total inversions 4, and then 10 and 2, yes, there is an inversion. So, total inversions 5. So, if we count the individual inversions of the blue part of the array or the blue sublist of the main list, we are going to have them as kind of 5 inversions in blue. Similarly, if we are going to count inversions in the right side, let us see. So, 6, 9, 6, 12, 6, 11 no inversions, 6, 3 is 1 inversion, then 9, 12, 9, 11, 9, 3 is 1 inversion, 9, 7 is another inversion. So, I have told you the method of counting the inversions. By this, if we count, so 5 blue inversions are there, and you can also kind of verify that there are 8 red inversions. So, within red list we have 8 inversions, within blue list we have 5 inversions. But our algorithm or our technique is not completed yet. We have counted individually the inversions in the blue list as well as inversions in the right list, but we are yet to count the inversions, the cross inversions basically, which are the inversions in between blue and red list. So, whenever we are going to count the these red list and blue list inversions, the count inversions after sorting, obviously after sorting the blue and kind of the red sublist, we are going to add the recursive counts plus the blue red inversion. Blue inversions were 5, red inversions were 8, and blue red inversions if I am talking about. So, there are, you can verify them, there are total 9 such inversions. So in totality I am having an total of 22 inversions, which are 5 plus 8 plus 9. So this kind of, we can say, lookout of this point of view of looking at this method of counting inversions was actually was lost or was hidden when we compare or when we take a very small example. This left side inversions, then right side inversion, and then there is kind of the cross inversions. This kind of point of view is available when you have at least large list of, let's say, at least 12-14 elements. So that's why we have taken one more example of this this method. Now another example, if for the sake of clarity, if we are going to take, what are we going to do in let us recall. Basically it is about merging and counting. So two sorted halves if we are given, we are going to count the number of inversions where ai and aj are in different halves, and then we will combine the two sorted halves into a complete sorted list. So here we have two lists again. So the first list says 3, 7, 10, 14, 18 and 19. Now please recall or please notice that the list is sorted. Both the lists on the left side or on the right side are sorted. The left side list is 3, 7, 10, 14, 18, 19, it is a sorted list. Looking into the right side, 2, 11, 16, 17, 23, 25 is also a sorted list. We will be taking all those inversions into our kind of counting, in which the element from the sub left array is greater than the element from the right array. So for example, let us say we are going to 3 and we are going to take 3 and 2. So yes, that is an inversion. Then 3 and 11 is no inversion, and then obviously there is no point in comparing 16, 17 as the arrays are sorted. Coming to the 7, if we compare with 7, then 7, 2 is obviously an inversion, 11 is not, and then we do not compare them on the further right side. Taking 10, so 10, 11 is no inversion, but 10, 2 is, yes, that is an inversion. Then 10, 16, 10, 17, 10, 23, 10, 25 are no inversion. So in this way, what do we need to do? This is a simple strategy as we do in merge sort. Here we have kind of two sorted arrays. What do we need to do? We just need to merge these two sorted arrays, and while the process of merging, we need to count these we can say inversions. So in the coming figures, you can notice that we have shifted 2 here in the sorted list, and then there were some inversions. Then we will keep on moving our pointers, and then the 3 element 3 is being shifted. Then we are going to shift element 7, because and in the kind of the lower half of the picture, we are actually giving the final sorted array, which is a combination of the merging of these two, which is the merge of these two sorted arrays. So then we will move on to 7, 7 is being shifted here, and we keep on counting those inversions. So here you can witness, and you can note down this example, and then also verify all the number of inversions which are being given here. So we have shifted 2, we have shifted 3, then we have shifted 7, and then 10. Then obviously 11 is being shifted, followed by 14, and total number of inversions is obviously is kind of getting incremented. So finally what are we going to get is this picture. So it is this. So finally we have 2, 3, 7, 10, 11, 14, basically a sorted list, a merging of the two above list, and the total number of inversions in this So, here in this example we have been given the sorted list, or the two lists which were already sorted, and what do we need to count is just the merge thing we need to perform and count the number of sortings. But in the previous examples we have not taken the sorted list, we have taken completely unsorted list, or we have also taken an example of the jumbled list. So, this was the method of modified merge sort which is used for counting inversion. In this lecture we in the inception we recalled what is our counting inversion is, what are the applications. Naive method we looked into in our previous lecture, we recalled it here. Then we looked into greater length of detail for this modified merge sort method, which is giving us a time complexity of order n log n, and we have seen some of the examples of this particular method. We have taken a completely opposite array, a small array, in order to understand this method. Then we start increasing the size of our examples, and in totality we have seen some few examples in order to understand this method of counting inversions. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.